It's David Spears, Civil Engineering Instructor at Texas Tech University, talking about solids, CE 3303. We're reviewing a problem from exam number 4, which was to do the basics of deriving an elastic curve and displacement, which the elastic curve really is, by integration method. Okay, we had this beam set up here, which is just kind of composite of all the 3 versions of the test. I have an 8-foot span beam with, over the first 5 feet, 12 pounds per foot distributed load and a 30-pound concentrated load at 5 feet from the left. I've called my points on there A on the left end, B in the middle, and C on the right end. And I've shown I'm going to have to write a curve for or an equation for the moment for each segment where the load doesn't really change. And so that means I have to write one segment for x1 distance measured from the left end until I get to the end of the uniformly distributed load and the concentrated load, and then I'm going to have to write another equation based on x2 distance from the left end. And first thing I need to do is solve for my reactions, and as always, some moments about a point I'll choose C, and counterclockwise is positive, so I have negative AY, assumed AY up, times 8, its distance to C, plus 12 times 5, the uniformly distributed load, times 5 times from its centroid to point C is 2.5 feet from this point B, plus 3 feet, and then I have my concentrated load, 30 pounds, times its moment arm of 3 feet. Both of those are positive because they are counterclockwise. I do a little bit of math and move the AY to the other side of the equal sign, and I get AY is equal to 60 times 5.5, which is that term right there, plus 30 times 3, divided by its 8-foot moment arm, and I get that AY is equal to 52.5 pounds. Now I do sum of forces in the Y direction, and I get that CY is the only unknown. It's got to be equal to my loads, 12 times 5, or 60 pounds, plus 30 pounds, minus my reaction at AY, so I get CY is equal to 37.5 pounds. Now I'm ready to solve for my moment equations, and I need to do free body diagrams to do that. So X from the left end, from distances 0 to 5 feet, here's a free body diagram. I have the beam, I have the load on it, 12 pounds per foot, and I have the reaction at A, 52.5 pounds. Okay, this X is X1 is the variable. So over here I have my internal moment, which I'll call M1. So I just do a sum of moments, and here's the section where I've cut it on the beam. Sum moments, counterclockwise positive, 0. So I have 52.5 times that X1 distance, whatever it is, the variable, and it's negative because it's clockwise, plus the distributed load force, which is 12 pounds per foot, times the X1 distance to give me the value of in pounds, times its moment arm of X1 over 2. Its moment arm from the centroid to this point over here, where I'm taking moments about, plus my internal moment. Rearranging, doing a little math, I get M1 is equal to 52.5 X1, really, minus 6 X1 squared. Whenever I can check something, I always want to do it, so I want to check at X1 equals 0, that my moment's equal to 0. Plug X1 is equal to 0 in there, and sure enough, my moment is equal to 0, so I feel pretty good about my equation. The second segment, after the load changes, is X2, and that's from 5 feet to 8 feet measured from the left end. Here's my free body diagram. Still have my reaction at A. I'm now off in this segment where I've cut the green line there. Now I'm between B and C, so there's no more changing of the distributed load, so I can just summarize it as 12 pounds per foot times 5 feet at 60 pounds. And I have my concentrated load of 30 pounds. I've noted here on my free body diagram, just for my convenience of calculations, the uniformly distributed load resultant acts at 2.5 feet from the left end, halfway from 0 to 5, and the 30-pound force acts at 5 feet from the left end. And of course I've got my internal moment, which I've called M2. Summing moments about 0.2, counterclockwise positive. I still have negative 52.5 times x2. That's its moment arm from here, from the reaction at A. It's negative because it's clockwise. Plus my distributed load, which is 12 times 5 or 60 pounds, times the distance from this point to the centroid of that resultant, which is x2 minus 2.5. So it's from here to here, x2 minus 2.5, plus my concentrated load of 30 pounds, acting at 5 feet, so the distance, my moment arm, is 30 pounds times x2 minus 5, plus my internal moment M2. Do a little math, combine terms, I get 0 is equal to negative 52.5 x2 plus 60 x2, which is 60 times x2, minus 150, which is 60 times 2.5, negative, plus 30 x2 minus 150 plus M2. Combining the common terms, I get 37.5 x2 plus minus 300 plus M2. So therefore M2 is equal to 300 minus 37.5 times x2. Always want to check that again. So I say at the end of the beam, I should have no moment. Put in x2 is equal to 8 into this equation, and that equals to 0. So, feel good about that equation also. We'll make this little correction here. That's x1 right there. Okay, now I'm ready to integrate that to get my elastic curve. Of course, I'm going to integrate these equations once to get my slope equation. And that's going to have a constant of integration, each one of those. And then I'm going to integrate it again to get my elastic curve or my displacement equation. That's going to give me another constant of integration here and another constant of integration here. But we didn't ask you to do that. We just went down to the boundary conditions and continuity equations, which are the key part of solving for those constants of integration. And we said do not solve for the constants. You didn't have time on this test. But we have 4 constants of integration, so we need 4 boundary conditions and continuity equations to evaluate it. So boundary conditions are things that occur at the boundary. They're the limits or the known quantities of things where usually at the edges or at the supports usually where we can evaluate these curves. Something I forgot to do and I've been not doing a good job of is draw the elastic curve on here. Looks kind of like that. It seems kind of simple and basic to do that, but it helps us remember things like our boundary conditions and our continuity equations. I observe that at support A, which is x1 is equal to 0, my deflection, or V, which I also call delta, is 0. So that's a boundary condition. My other boundary condition is over here at the other end at point C, where x2 is equal to 8. My deflection is also equal to 0. So that's all I wanted on that. Continuity equations are things that occur in the continuous nature of the beam. And so think about that, continuity, continuous. So I observe that where I switch from x1 to x2, my elastic curve is just it's a number, the deflection. And so at that point where x1 is equal to x2 was equal to 5, at 0.5 feet from the left end, my deflection from equation 1 that I derived from my moment 1 is going to be equal to the deflection that I derive from moment 2 equation. In other words, my deflection or my delta is the same at 5 feet. Similarly, at the same point, x equals 5, my slope has got to be equal to the same. So I've written it this way. It just means my slope is the same from both equations.